So in today's video, we're going to go ahead and take a deeper look at u-substitution, and we're going to see how we can actually define u in a way that makes the integration process much simpler. And so really the whole notion of u-substitution comes from integrating the derivative of a composite function. And so we know that when we're differentiating a composite function like f of g of x, right, over here, then that's just going to be the derivative of the inner function times the derivative of the outer function evaluated at the inner function, right? So g prime of x times f prime of g of x. And this is just the chain rule over here. And so u-substitution can be thought of as kind of like the reverse chain rule, where we're taking a function that's in the form of the chain rule. It's in this chain rule form over here, and we're kind of just taking the antiderivative of that. So we're reversing the chain rule here, if you will. And so let's actually go ahead and apply that to a couple of examples, because really when we want to use u-substitution, we kind of just have to see where we can find this sort of form of the derivative of the inner function times the outer function's derivative evaluated at the inner function. We need to find that form over here. And so let's actually go ahead and do that with a couple of examples so we can get comfortable with this notion of defining u in a way that really simplifies the integration process instead of actually ending up with a more complicated integral. And so over here we have this indefinite integral. We have 3x squared plus 18x plus 7. And then that's just being multiplied by e to the x cubed. So e to the x cubed plus 9x squared plus 7x minus 10. And so this looks like a very complicated and intense integral, but really we just have to observe something over here. We have e raised to this very intense looking third degree polynomial, but then over here we have the second degree polynomial that's multiplying e. And so let's go ahead and see what happens if we let u be equal to x cubed plus 9x squared plus 7x minus 10, right? So we're just letting u be equal to this third degree polynomial that e is being raised to. And then let's go ahead and differentiate both sides with respect to x. We'll end up with 3x squared plus 18x plus 7. And then we multiply both sides by dx. We get du is equal to 3x squared plus 18x plus 7, and then we have dx over there, and it's multiplying the whole expression. And so now what do we have? Well, we have this third degree polynomial that we described in terms of u, or that we wrote, or we set u to be equal to. So we defined u to be this third degree polynomial that e is being raised to. And then over here we have 3x squared plus 18x plus 7, and we're multiplying that by dx. Well, that's just going to be du, right, based on this substitution. And so if we want to put everything together, we ultimately end up with e to the, here we have this third degree polynomial, we set that to be equal to, so this just becomes e to the u. And then we have this second degree polynomial times this dx, we just said that that's going to be equal to du. And then if we wanted to evaluate this, it's very easy, we can just get e to the u plus c. But we want to get this back in terms of x, and so we can just go ahead and resubstitute, and we end up with e to the x cubed plus 9x squared plus 7x minus 10, and then plus c over there. And we really don't care about the answer here. I kind of just want you guys to get more comfortable with how to actually define u in the most optimal manner. So we took a very crazy and intense looking integral and simplified it into something as simple as e to the u du, and then we just resubstitute back in, and that's our final answer. And so we have to define u in a way that makes the integration process much easier, just like we did in this particular example. So let's go ahead and take a look at the second example over here. We have the indefinite integral of x times x squared minus 1 to the 7th power. And so we could expand this, 7th degree binomial expansion over here, and we just get a whole bunch of terms and it'll be a big mess. Or we can just use a very smart substitution over here. So we have x squared minus 1, and we're taking that to the 7th power. So it could be helpful to make that just one simple term, just a single term that we can let u be equal to. So we can say u is equal to x squared minus 1, right? And then du by dx is just equal to 2x, which implies that if we multiply both sides by dx, by that differential, we get du is equal to 2x dx. And now this we really have this over here. We just have to do a little bit of manipulation. So we have this x squared minus 1, we have this dx, and we also have an x over here. We just need this x over here to become a 2x, and so we can just multiply by 1/2 on the outside, and then multiply by 2 on the inside of the integral, and then here we still have this x squared minus 1 to the 7th dx. We have a 2x here, a dx. We have this x squared minus 1, and that's being raised to the 7th. If we put it all together, we ultimately end up with 1/2 times the integral of this x squared minus 1 to the 7th. That's just going to become u to the 7th, right? Because we said x squared minus 1 is just equal to u. And then 2x dx, we said that that's just equal to du. And so we end up with 1/2 times u to the 7th du. And then ultimately, we just use the reverse power rule. We get u to the 8th over 1/2 times 8 is just 16. And then we have plus c. We want to bring this back in terms of x, and so we can just resubstitute, and we get x squared minus 1 to the 8th over 16 plus c. And that's our final answer right over there. So we took this very intense looking integral as well. We used a smart substitution here. We kind of just set u to be equal to this expression over here that we're raising to the 7th power. So we don't really have to expand anything. We just have to know how to substitute correctly. And then this final example over here that we're going to take a look at, we have the indefinite integral of 14x cubed plus 3x over the square root of 7x to the 4th plus 3x squared plus 9. And then again, we just have to know how to substitute correctly. So we have this term in the denominator, we have this term in the numerator, and I'm actually going to go ahead and let you guys explore this one for yourself. See the most optimal way to actually set u over here and just do a little bit of manipulation, right? And if I'm correct, you should ultimately end up with, this should be 1/2 times the square root of 7x to the 4th plus 3x squared plus 9, and then plus c, if I'm correct. That should be 1/2, 1/4. Well, actually, you don't really need that 1/2. Okay, there you go. That will be your final answer right over there. My apologies. But yeah, go ahead, try this integral out for yourself and see the most optimal substitution to ultimately end up with your final answer.